Okay, so welcome back. Happy Friday. Today we are going to talk about absolute and conditional convergence and see something called the absolute series test. Today, I will get to that. All right. So today is our very last day of series tests. We have seen a whole slew of them over the last few classes. This is the last day of new series tests. After this, you can see we're still talking about series, power series and Taylor series, but things will start to look different starting on Monday. Also, Project 7 is due right now, so throw it in the folder. And I will hand out the quiz at the end of class today, and that will be due on Monday. And also Monday, Project 8 will be assigned. Questions on the calendar? Okay. So, Rich and some others recognized that I misassigned a problem in last night's homework. It should have been in tonight's homework. So maybe just kind of copy that down or make a note that number 35, which maybe you did last night, should have been assigned tonight, right? So take it off of last night's homework and do it as part of this homework right here. Sorry about that. Last mistake all semester. Okay, so we'll go to the daily summary. Can we start with Steve? Okay, so number one, is it true or false? It says if the sum of the absolute value of a sub n's converges, then the sum of the a sub n's without the absolute value also converges. Let's think about this. So suppose that you have, this semester, almost all of the series we've been talking about have just been positive the whole time. Occasionally we'll have one that alternates between plus signs and minus signs, but most of them have just been straight positive. But suppose you do have some with some plus signs and some minus signs. And when you take the absolute value of every single term, which is what the first series says, which means they're all plus signs now, suppose that you add all of these things up forever and it converges. It's something finite. Now suppose that you allow some cancellation. You bring these negative signs back in like in the second series there. Will it still be finite or might it be infinite?
The absolute value the absolute value of a sub n is positive.
Isn't that true? The absolute value is going to be bigger than the original? If you add up all these positive numbers and it's finite, and then I allow some of them to be negative, well, it's going to be more finite. If I mean, that phrase doesn't have meaning, but there's going to be cancellation, right? If it was already finite before when everything was positive, and now all of a sudden I allow some negatives in here, then it's going to be even smaller than it was before, right? So it's going to be finite as well. So this is a true statement, and the statement above is called the absolute convergence test. If you can take the absolute value of a series and it converges, then automatically the original series also converges. So let's take a look at this particular series right here. The sum of -1 to the n over n squared. As is my tendency when I see a new series, I write out the first few terms just to get a feel for what's happening. N equals 1. That's -1 to the first, so that's -1 over 1 squared. And then we're doing n is 2. So when I do -1 to the 2, it becomes +1 over 2 squared. Next one. -1 over 3 squared. And then a +4 over 4 squared, and then a minus ... So called an alternating series because it alternates between plus and minus. Every other term is positive, every other term is negative. This, seriously, my last mistake. Like, no joke. No joke. Right. Okay. So I don't know what's going on with that series. It's the first time I've seen it. But if I take the absolute value of all those terms, then everything becomes plus. And we've seen that series before. So if I look at the, I'm going to copy it just as it is. And then I'm going to throw the absolute value around it. And if you throw the absolute value around it, then the -1 to the n just becomes straight 1 every time, right? So this is really just 1 over n squared. And that is a p series, and we just got to recognize the form of the p series. How much is p? So it's I'm going to leave a little blank here. It's a blank p series where p is equal to 2. What's the magic number for p series? Is 1. 2 is greater than 1, therefore converges. So it's a convergent p series. So what does that mean about red? Convergent, right?
Now, if the blue was
Yeah, if blue is divergent, it doesn't help us. Yeah. Okay, so then, so the sum of the original guy, n over n squared, converges by the absolute convergence test. Sure. Yeah, yeah. Okay, so there are 2 series tests we're learning today. That was the first one. The second one is a lot more involved than the first one. So here it is. It's called the alternating series test. It's number 3. So if you have a series of this form, -1 to the n plus 1 a sub n, which means a1 minus a2 plus a3 minus a4. It's just an alternating series, but written generically. And if it happens that the terms are getting smaller, that is to say, the next term is always less than the previous term. Another word for that is that the sequence is decreasing, yeah? So that says the terms are getting smaller. And if the terms go to 0, notice that the -1 is not part of this anymore. So if the terms are getting smaller and going to 0, then this brand new test, alternating series test, tells me that the series must converge. Yes, then it converges. So it's basically 3 conditions: alternating and decreasing to 0. The series converges. Yeah, the terms are going to 0. So here's why that is true. Suppose that we look at this diagram right here. So so starting at 0, I'm going to add a1, and I'm going to land over here at what we're calling the first partial sum. We saw this notation earlier. S1 is the first partial sum. And then I'm going to add a2, except it's a subtract, right? Because of the way this alternating series is set up. So if adding sends me to the right, then subtracting must send me to the left. So from the current partial sum, I go this far, which you'll notice is less than the distance we traveled in A1. That's the decreasing part. Okay, so then I'm now over here. That's my second partial sum. And then we're going to go to the right, but not as far as we just went to the left. And that lands me here. And then we'll go left, not as far. And do you buy that if we do this forever, the answer is going to be someplace in there, right? It can't possibly be infinite. And it also has to hone in on a single number because we keep moving left and then right and then left and then right, right? Smaller and smaller every time. So we have to hone in on something in that fuzzy space. I guess technically it's someplace in there is where it is. No, it doesn't have to be anything nice multiplied by a1, but it's just someplace. It's something finite and it's a single number. Rob. The n plus 1 just makes the first guy positive. Starting at n equals 1. It doesn't matter. No problem. Yeah. Yeah, the a sub n plus 1 less than an means the next one is smaller than the previous one. And that's this honing in. Okay, so let's try number 4 here. It says write out the first 5 terms of each series and determine whether or not each series converges. Okay, so let's write out the first 5 terms of this guy. So beginning with n equals 1, I get -1 to the 2, which is positive, right? So that's 1 over 1. Then we plug in n equals 2, and it's -1 over 2. And then n equals 3, positive 1 over 3. Write out the next 2 terms. That's what it's called. So Elia, louder. Yeah, so we'll do that in a second, Lynn. So yeah, it's the harmonic, but alternating, right? Okay, so let's use our alternating series test. We need 3 conditions. It needs to be alternating, is it? Yes, and as soon as you see that -1 to the n plus 1 or to the n, it's alternating. Are the terms decreasing? Is every term, if you forget the pluses and minuses, we just make them all pluses. Yes, these terms are getting smaller and smaller, and are they limiting to 0? Yes, and the 3 conditions are met, therefore that series converges. Now you don't just get to write converges or even converges by the alternating series test. You have to tell me that you have verified that it meets the 3 conditions. So, but you can pretty much bully me into believing it. You just have to say it. So in this case, we know that a sub n plus 1 is definitely less than a sub n. The terms are all getting smaller. And limit as n goes to infinity of 1 over n. That's ignoring the -1 part. What is this limit? 0. Those are our conditions, the alternating part, and you can just see that it's alternating. As soon as you quote the alternating series test, I'm assuming you know you're talking about an alternating series. So by the alternating series test, and then we copy that series, converges. Great question. I don't know. Some of the alternating harmonic series. Anything? Ln of 2. That's what the alternating harmonic series converges to. Ln of 2. All right. So what was the question here? Yeah, so I'm being really lazy, and you can be lazy too with the sigma notation. I'm not super concerned with the starting point. It's really the infinity, and it's implied with everything we do. So you don't need to write it. Okay, so we're gonna do what Len had suggested a couple minutes ago. What is that? Okay, so Len had thought about taking the absolute value of these terms. So if we take the absolute value of these terms, then what series do we get? The harmonic series. And does that one converge or diverge? It diverges, which is different from what the alternating one does. So unfortunately, it doesn't help us, right? Like just because the absolute value version diverges doesn't tell us anything about what the original version does. Len, did you have another? Okay. All right, let's take a look at this guy right here, part B. So I see the -1 to the n. I'm not bothered that it's not an n plus 1. It doesn't make any difference. So it's definitely going to be an alternating thing. But before we jump in and start talking about the decreasing and the tending to 0, let's just look at what these terms are doing in the long run. Limit as n goes to infinity of -1 to the n over n plus 1. Just looking at the limit of the terms. Forget the -1 part. What happens to the second parentheses? Right? Doesn't this part right here go to 1? So the whole thing, so then I'll just put ×1 because that's what the second part goes to. So then the thing is really -1 to the n, and what about that limit? It doesn't exist. It's -1, it's +1, it's -1, it's +1. So this, so it doesn't exist. And I think Elia was talking about the nth term test for divergence was one of our very first ones. In order for the series to have any chance of converging, what do the terms have to go to? They have to go to 0, right? Because you're adding infinitely many of them. And these terms are not going to 0. They're essentially -1 + 1. So what do you think about that series? It does not converge, diverges. What's that, Alex? Yeah, so this guy right here diverges by the nth term test. So you'll get some area that looks like it just straight cancels forever. You'll have basically a rectangle at the top that's like a 1 and a rectangle at the bottom that's a -1. And sometimes it's 0 altogether and sometimes it's 1 altogether, and it never hones in on a single number. Yeah. Okay, so this example is here to highlight, hey, just because you see that -1 to the n doesn't mean you should begin with the alternating series test. First thing I do with any series is this test. Do the terms go to 0? If not, it's an easy win. Okay, so that is the alternating series test. Number 5 talks about an error calculation. Let's go to Gabe for 5. Go ahead. Okay, so first, when I looked at this the other day, I realized that I had left out some conditions. You can add them if you want. You don't really need to. I'm assuming that we're looking at one of these alternating series that met our conditions from a second ago, that the terms are decreasing and going to 0. So if we're in that case with the funny picture going back and forth, smaller and smaller, then we can tell what the error is going to be by stopping this series at some point. And it turns out if you stop it at a sub n, then the error, how far you are from the right answer, the infinity answer, is a sub n plus 1. I'll show you the picture here. You guys agree that that the right answer, if I did this sum forever, is something between S3 and S4, right? And that distance is A4, yeah? And so if I stop at A3, if I stopped right there, and I said, okay, this is my best guess for what the real infinity answer is, at most, I am off by A4. It's someplace in that next range, right? And if I stopped it a few terms later, the range would be smaller and the range would be whatever the next term is. So you can stop it after 100 terms. How far you are from the right forever answer is less than the 101st term. So let's take a look at how to use this in number 6. So this is the series we looked at just a moment ago. So if we did this first few terms, which we wrote out before, so it was 1 over 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus ... right? So if I just stopped it here after 4 terms, then the error is definitely less than the next term, the 5th term, which is 1 over 5 squared, 1/25th. The negative is accounted for in the negative. It's the a sub n that we're after. Where is it? Here. The a sub n's have the -1 pulled off to the side. So the a sub n's are the positive things. Yes. Yes, that's the magnitude of the error, is less than 1/25th. So if we actually did this, so let me just do a quick calculation to show you what we mean here. If I actually add these things up, so 1 minus 1/4 plus 1/9 minus 1/16, is that right? Okay. So this is our estimate for the series going forever. It's a very rough estimate. We only did 4 terms. Should have done 4 trillion terms. But we know that how far we are from the right answer, the forever answer, is definitely less than 1/25th. And because we happen to look this up, we actually saw on that web page that ln of 2 is the right answer if you let it go forever. And are these things less than 1/25th apart? We did. What happened? 1. Oh, yes. The ln of 2 was not this one. The ln of 2 was the alternating harmonic series. Right. Yeah. So forget that. But what we have seen. So I don't know what the right answer is to this guy forever, but I can. The harmonica. So we know that the correct answer is no more than 1/25th bigger than that number right there. Yeah. Yeah, I mean that's totally fine. So so you just have to get to a place where you're happy with the margin of error, and this gives you a very easy way to tell what the margin of error is. Yes, it is possible to make it so that it's not an alternating every term, but it's plus plus minus minus plus plus minus minus. But not today. Not today. Not today. All right, so last couple of things here, just some vocabulary. If the absolute value of some series converges, then we say that the series by itself without any absolute value is called absolutely convergent. We saw an alternating series today that when we put absolute value around it, it still converged. Was that the over n or the over n squared? Over the n squared is the one that we saw, right? That was the very first example we did. We put the absolute value. We didn't put the absolute value around the over n one. We put it over the n squared one. So this guy right here over n squared is called absolutely convergent. It really totally converges, but that's not the meaning of absolute. We're talking about absolute value is what it means. But it totally converges, right? Because it converges even without the alternating piece. Even without that cancellation, it still converges. Okay, but if you have a series where when you put the absolute value, it diverges, but if you allow some cancellation, if there's some negative stuff happening, if it converges in that case, then the series here is called conditionally convergent. That is a weaker statement. This -1 over n, the alternating harmonic series, it converged, yeah? But if you put the absolute value, what series did we get? The harmonic, which diverged. So what do we call this thing right here? Conditionally convergent. You don't need, I'll go out of my way to ask you to classify it if I wanted you to. Yeah. So that one is conditionally convergent. It only converges on the condition that you let some cancellation happen. We need those pluses and minuses to cancel with each other. Because if you try to make them all pluses, it diverges. So every convergent series has a margin of error for any stopping point. But there's a really simple formula for finding that margin for alternating series. that doesn't exist for just generally convergent series. This is an alternating, it was that picture was the key, was that you keep going back and forth, and so you're honing in and it's just this little tinier and tinier spot. But for a general convergent series like the 1 over n squared just by itself, if you go 100 terms out, I don't know how far you are from the answer. We keep getting bigger and bigger and bigger, plus, plus, plus. Okay, so here's the last thing, and then we'll do the activity. Okay, 1 minus 2 plus 3 minus 4 plus 5. How does that compare to 1 plus 3 plus 5 minus 2 minus 4? Don't do the calculations. Just look at the numbers in both series, and how will the sums compare? Got to be equal, right? Just look at the signs of each number. The 1s are both positive, the 2s are both negative, 3s are positive, 4s are negative, 5s are positive. So they're the same, right? So of course, it makes no difference how you add them. They're just the same number at the end. Sadly, this is not true when we go to adding infinitely many terms. It's true when you add 5 or 5 trillion. But if you add infinitely many terms, some funny things can happen. So check this out. 1 minus a half plus a third minus a quarter forever. That's our new friend, the alternating harmonic series, yes? Okay, I'm going to rearrange this in a very funny way, but all I have to do is convince you that every term in the original is there in each of these subsequent expressions. Okay, so that one is copied down there. The minus a half is copied there. I'm going to shuffle the minus a quarter and minus a third. I'm going to put the minus a quarter there, and then the 1/3 is going to be here. The signs are all copied correctly, yeah? We're just shuffling them around. You had no problem when I shuffled the terms up above. Okay, now the 1/3, I want to pair it with the 1/6. You can see that there's like this parentheses thing happening. And what I want to do is make sure that the numbers that I pair are doubles. So the 3 went with the 6, the 5 went with the 2. That's why the 5 and the 10. That's why the 1 went with the 2. And then the other numbers that aren't appearing here are going to be these multiples of 4. So let me circle some different stuff. Here are the, what kind of numbers? What kind of numbers did I just circle? Odd numbers, right? Those are the odd numbers that I want leading every parentheses. When I double them, those will be some of the even numbers, but there will be other even numbers that I need to capture, and these are the 4ths and the 8ths and the 12ths. So do you buy that it's a forever thing, and so some of these terms might get shuffled pretty far, but do you buy that every term in the beginning is going to end up someplace down in the next line? Okay, now we're going to do some calculating. 1 minus a half is a half. This minus a quarter is straight copied. I'll just point to the minus an 8th and a minus a 12th while we're at it. How much is a third minus a 6th? Isn't it a 6th? Right, because that first one is 2 6 minus 1 6, so that's there. How much is a 5th minus a 10th? That's a 10th, so that's there. We buy it? Okay, now I'm going to factor a half out of everything in this new thing. So pull a half out of the first guy, what do we get? 1. Half out of the next guy is minus a half. Half out of the next guy is plus a third, so I've written that in here. Yeah? But this thing in the parentheses is what? That's the alternating harmonic, which is quite troublesome because we started with the alternating harmonic and saw that it was equal to half of itself. So what I'm saying is that our idea that look at the top example there, that when you're adding these 5 numbers, you can just shuffle the order and add in any order. That's true if you are adding finitely many numbers. But it turns out that if you rearrange the terms in a conditionally convergent series, infinitely many things, but only conditionally convergent, not only can you change the sum like we just did there, we made the sum equal to half of what it was, but it turns out that you can make the sum equal to any real number at all. Minus 1/12. It's the number. So maybe you've seen this number file video, right? We just watched it. Oh, we should watch it. At 2:10, we'll put it right up. So again, really wild. But any conditionally convergent sequence, you can rearrange the terms in a way that the sum will actually be any number you want. You can make it equal pi or negative 112, 517. Half of what it was. Anything. Gabe. So I think this is supposed to be the same as that. You got to let it go forever. I mean, like it might take some more terms to actually see the all 12 that I've got up there. But if we let it go forever, it's every term is accounted for. Well, there's no quantity. It's infinitely many things. I'm just writing a few of them to illustrate what's going on. Yeah. Okay. Activity starts on the next page. Raise the flag if I can help.